We continue our lecture on transport phenomena in furnaces, fluid flow, that is where we were discussing. We have derived mechanical energy balance and we had applied this mechanical energy balance to design the head meters. The head meters with which we have considered were orifice, venturi and nozzle. The respective energy balance equation were already derived. Now today I will illustrate it by solving few problems so that you understand the various parameters and their substitution. So let us consider first of all, say compressed air at 7.2 into 10 to the power 5 Newton per meter square pressure and 350 Kelvin flow through an orifice plate installed in a 90 millimeter internal dia pipe. The orifice plate has 30 millimeter hole. Now, if the manometer reads, say if the manometer reads 360 millimeter mercury pressure, calculate flow rate of air. Calculate flow rate of air and calculate A, for example, flow rate of air, and B, permanent pressure drop. Now, as you recall, here the orifice dimensions is given, it is a 30 millimeter hole, but from the manometer or from the consideration of the fluid flow lines through an orifice, all of you are aware that the minimum cross sectional area is not the diameter of the hole, but some distance downstream the hole, and hence the diameter is somewhat lower. Accordingly, in this particular problem, if we know the coefficient of discharge value, then we can proceed with the problem. So, as such, assume CD, that is the coefficient of discharge for this particular orifice, that is equal to 0.61. This is for orifice. So, let us proceed to solve this particular problem. Now, what is given is, say this is the pipe, this is for example a center line, and somewhere here a plate of say 30 millimeter hole, that is 30 millimeter phi, and the diameter of the duct is 90 mm phi, and P1 that is equal to 7.2 into 10 to the power 5 Newton per meter square pressure, 350 Kelvin, and air is flowing through this pipe, and we have to find out the flow rate of air and permanent pressure drop. Now, straight away we can use the expression which we have obtained from mechanical energy balance, the mass flow rate through the orifice. So, we got this equation, for example, mass flow rate through the orifice, that was equal to K Y A0 2 rho P1 minus P2, where P1 minus P2 is the pressure differential, K is the flow coefficient, Y is the expansion factor, and A0 is the cross sectional area of the orifice. So, now we proceed to calculate the different parameter. As we know that K that is equal to CD upon square root of 1 minus B to the power 4, and B is the ratio of the diameters. So, CD is 0.61 upon 1 minus 30 upon 90 raised to the power 4. This is square root of that. So, if we solve, we will get K that is equal to 0.614. So, we got one variable K. Now, we can calculate also Y. Now, as you recall, Y was the expansion factor, and this equation is that kappa 1 minus P2 upon P1 raised to the power kappa minus kappa 1 minus B to the power 4 upon kappa minus 1 minus P2 upon P1 P2 upon P1 raised to the power minus 2 upon kappa minus B4. So, all that we have to substitute the values, but we have to find out P2 and P1. Now, P1 we have to find out this way. Say P1 is given 7.2 into 10 to the power 5 Newton per meter square, and P2 is somewhere at the exit. So, P2 will be equal to P1 minus the pressure differential, which is 360 millimeter mercury, when multiplied by conversion factor into Newton per meter square. So, that is equal to 7.2 into 10 to the power 5 minus 0.48 into 10 to the power 5. So, P2 is equal to 6.72 into 10 to the power 5 Newton per meter square. Now, since P1 is 7.2 into 10 to the power 5 Newton per meter square, the manometer records 360 millimeter of mercury as the reading of the, that is the pressure differential. So, hence P2 will be accordingly less than P1. That is how the gas will flow. That means that fraction of the P1 is converted into the velocity. So, now we know the value of Y, we know the value of K, we know the value of A0, which is pi by 4 d square, and so on. So, now we can calculate. So, first we evaluate the value of Y. So, I do not think I need to substitute. Well, you can do well. Let me substitute for you. You know kappa is isentropic exponent, which is 1.4 for all diatomic gases. So, I substitute 1.4 1 minus 6.72 upon 7.2 into 10 to the power 5 into 10 to the power 5, that is raised to the power, this is this one, 0.286, 0.987, that is the value of 1 minus b to the power 4, that is equal to 0.4, 1 minus 0.933, 0.933 raised to the power minus 1.428 minus 0.013. So, if you solve, this y value is equal to 0.924. Now, we know this thing. Now, we can proceed to calculate. Say we have to calculate also rho. Rho will be equal to say 7.2 into 10 to the power 5 is our pressure. If we divide by the gas constant and the temperature is 350. So, this value is 7.176 kilogram meter cube. So, now we know all the value. Now, I can substitute into the expression. So, this m will come out to substitute, it will come out to be equal to 0.33 kilogram per second, and this is the answer for the flow rate of air. That is how you can see, by installing a manometer and orifice in a pipe, one can calculate the flow rate of air. Now, since as I have said that because of the formation of vena contracta, there is a heavy loss of pressure when the air flows through the orifice. So, let us calculate, and this pressure drop is permanent in nature. That means, you cannot recover this pressure once it is lost because of flow through an orifice. So, that is why you call permanent pressure drop, and permanent pressure drop that is equal to, you recall the formula, 1 minus b square into P1 minus P2. So, we already know the values, and if I substitute, I will be getting the permanent pressure drop is 0.43 into 10 to the power 5 Newton per meter square. So, that is what a typical of the orifice meter, which shows a substantial amount of loss of pressure when, for that matter, any fluid, air or water, it flows through an orifice. Now, let us take an example of a Venturi meter. Let us consider a Venturi meter of throat diameter of 250 millimeter is installed in an air duct of circular cross section of diameter 500 millimeter. The duct carries air at 1.28 meter cube per second, which is given at 298 Kelvin and at pressure 1.1 into 10 to the power 5 Newton per meter square. Now, determine the maximum pressure drop, that a manometer can handle. Manometer can handle. Now, as I have said that Venturi meter, they are designed such that there is insignificant loss of pressure and hence their coefficient of discharge value for calculation purposes. So, take CD that is equal to 0.98. So, now we have to calculate what is the maximum pressure discharge. So, in fact, the problem can be illustrated this way, that this is the duct of circular cross section, and well, somewhere here is the center line, and we are installing a sort of Venturi meter This is the Venturi meter installed in a duct, and this Venturi meter, this is its cross section area, throat that is equal to 250 millimeter 5, and the duct has 500 millimeter diameter. So, for this particular case, the manometer is installed at position 1, and here, since there is no vena contracta formation, the flow is very straightforward, and so the manometer 2 plug will be here. So, in between 1 and 2, manometer is installed. Manometer is installed. So, we have to, for this condition, when say air is flowing say 1.28 normal meter cube per second, air is flowing at 298 Kelvin and 1 atmosphere, that is given to us. So, we have to calculate the so called the maximum pressure drop. So, now let us proceed. So, we know the equation, because there is no difference in the equation that we have obtained for mechanical energy balance, though we have said it is for the orifice, but in fact it relates the diameters, that is the pipe diameter and the diameter through which the flow passes. So, the same equation will be valid. So, M we know is equal to K y A0 2 rho P1 minus P2, that is our equation. Now, first of all we have to calculate the value of K. So, K straight away we can calculate. You know this formula, CD 1 minus b to the power 4 square root. So, substitute the values. So, K will be equal to 1.012. Similarly, I can calculate the density also, that will come 1.288, you calculate yourself. Similarly, I can calculate the velocity v, that will be equal to q upon a. So, A0, where A0 is the minimum cross sectional area of Venturi, minimum cross sectional area of Venturi, that is given 250 millimeter. So, if we calculate V, that will be coming out to be equal to 26.09 meter per second. So, we know all the values. Now, here Y is not known to us. Y is not known to us. So, we can, let us say assume say Y is equal to 1, but this assumption has to be verified once we calculate the pressure differential. So, if we assume Y is equal to 1, then we can calculate now. So, we can just rewrite the expression, say P1 minus P2, that is equal to m square upon k square y square A0 square into rho to 2. So, now all the variables are known. So, if I substitute the values, you can just substitute the value of m will be equal to what? M square, that will be equal to rho square, V square, A0 square. So, you can further simplify if you wish, 2k square y square A0 square into rho. So, that will be equal to rho V square upon 2k square into y square. So, if I substitute the value, I will be getting 424.67 Newton per meter square, that translates into 43.3 millimeter H2O. So, in fact, that is my answer, that is a manometer can handle 43.3 millimeter of water as the maximum pressure difference. Now, this answer is subject to the validation that y is equal to 1. That means, the answer or the solution of the problem is incomplete at this stage, because we have made assumption y is equal to 1. So, we have to now, since we know the pressure difference, now we can calculate the value of y. You know the formula for y, say P1 now is given to us 1.1 into 10 to the power 5 Newton per meter square. So, P1 minus P2, that is equal to pressure difference. So, P2 that comes out 1.095 into 10 to the power 5 Newton per meter square. What I could do? I can substitute. So, P2 upon P1, that is equal to 0.996. Well, I left this exercise of substitution, the various parameters that are involved in the calculation of y, and I straight away write down that the value of y that we are getting is approximately equal to 1, and hence assumption is verified. Assumption is verified. Now, if you do not want to make any assumption, then you can substitute the value of y, that is the formula, into the expression. Now, in the expression P2 upon P1, that is the only variable, rest is all known. So, by the method of iteration, you can also find out the value of P2 upon P1 or the pressure differential. That is also one of the technique to find out. So, now with this we have verified the assumption, hence our answer is okay, there is no problem at all. Now, let us see another problem from this. Say what we are doing now, say instead of Venturi, instead of a Venturi, an orifice meter is placed. An orifice meter is placed, or rather is proposed to be installed. In the previous problem, all the things are same in the previous problem, that is duct of diameter 500 millimeter and so on. Now, what is required? Calculate the diameter of a sharp edge orifice, of a sharp edge orifice that should be installed, that should be installed to obtain manometer reading of 50 millimeter. Take CD for this problem of orifice equal to 0.262. Now, note that the CD is different. For Venturi it was 0.98, for orifice we are taking 0.62. So, the flow rate, pressure, everything is the same. Now, we have to calculate an alternative proposal that, well, Venturi is not available. Let us see if I can work with the orifice. So, I have to calculate now. So, if I do that, I straight away we can write down the formula M, that is equal to K Y A0 2 rho P1 minus P2, that is what we know. Now, from here we can say that A0, that is what we have to find out, that will be equal to rho Q, you can derive this expression, K into Y 2 rho P1 minus P2 raised to the power 0.5. So, now here again the value of y is not known. So, here again y has to be assumed, value of y has to be assumed. Rest all parameter you can calculate, we have done already. So, if I substitute all the variables over here, then I will be getting, now note here the B is also not known because K is equal to CD. So, we have to calculate the value of B that is equal to D2 upon D1, hence K that will be equal to CD upon 1 minus B to the power 4 square root. B we can't calculate since D2 is not known to us. So, K will simply become equal to 0.62 upon 1 minus B to the power 4 the square root of that term. So, now we can substitute all the variables. So, I calculate now A0, that will be equal to 0.0753 1 minus B4, that is what we will get it. Now, we have to solve it. So, we can do that now square. So, A0 square, that will be equal to 0.0057 1 minus B4. So, now I can calculate, I can put A0 pi by 4 D0 square, I can calculate now a simple expression. So, D0 that will be equal to 0.299 meter, D0 or D2 whatever you want to call, that is equal to 0.299 meter or approximately 0.3 meter. Now, here we have assumed y is equal to 1. So, you have to verify. You have to verify. Please use the appropriate expression for y for orifice. and verify it whether you get y is equal to 1 or not. Now, I give you further for you to calculate. So, for the same flow condition, calculate the orifice diameter for the following conditions. Now, A, when maximum pressure drop, across the manometer, is 60 millimeter water. B, same when pressure drop is 70 millimeter water. C, same when pressure drop is 55 millimeter water. The idea is that to know how the pressure drop varies with the orifice diameter. So, I expect this to be a sort of non-linear, and then I ask you to plot also. So, plot the result as, for example, take on the y axis a pressure drop, and here you take orifice diameter. My calculations yielded me, say, delta P, we have 50 millimeter, 55 millimeter, 60 millimeter and 70 millimeter water. Orifice diameter in meter, that 50 millimeter we have already calculated 0.299, for 55 0.293, please calculate it, and 0.287 and 0.279. So, I expect some sort of a non-linear relationship. Now, let me go to the next thing, that is the draft. Draft at any point in the gas flow system, it can be is equal to absolute pressure in the system minus absolute pressure of the surrounding atmosphere, at the same level. So, if we take D1 at one point, that will be equal to P1 naught minus P1, and D2 at the point 2, that will be equal to P2 naught minus P2. Now, it is also important, since small pressure differences are controlling factors in the furnace system. So, variation of pressure with height in a gas column is important. You consider the gas column of certain height, then accordingly the pressure exerted on a particular point will be influenced by the height. So, as such, it is also important to consider the variation of pressure with the decrease in height, and the variation of pressure with the decrease in height say variation of pressure with decreases with height, it can be represented as dP, that is equal to minus rho into dz, where rho is the density of gas in the column, is the density of gas in column of height Z1 and Z2, that is Z2 minus Z1. So, with this we can say P, that is pressure at any point, that will be equal to P0 minus rho into Z. So, this is the equation which tells you the effect of a column of the gas on the pressure. Now, in this expression, say P is pressure at height Z, and P0 is pressure at the arbitrary datum plane of 0 height, So, let us now consider natural draft. Now, natural draft is created by the difference in density of gases, by the difference in density of gases. Now, let us consider a vertical column. So, this is a vertical column. Let us consider a vertical column of hot gases, that is, this column is filled with hot gases are flowing, is filled with hot gas, the gases are not flowing, and this column of hot gas is surrounded by air at ordinary temperature and pressure. Manometer at height Z1 and Z2 are installed to measure the relative draft at two levels. That means, this is the manometer this is also manometer. They are installed at location 1 and 2 to read the relative draft. The average density of hot gas, let us say, is rho h, and that of air is rho a. So, what we are considering now in finding out an expression for natural draft, we are considering a vertical column of hot gas, the gases are not moving. We have installed two manometers at two different positions at Z1 and Z2 to measure the relative draft. Now, this vertical column is surrounded by air at ordinary temperature and pressure. So, we can write down now P1, that is equal to, as per the definition, P01 minus rho h Z1, that is P1, that is the pressure at this particular point will be absolute pressure at this point plus this pressure of this column. That is what I have written, P01 minus rho h Z1. Similarly, the pressure at point 2, that is P2, that will be equal to PO2 minus rho h Z2. Now, we have to define the draft D1, that is equal to P1 naught minus rho a Z1 minus rho h Z1, and D2, that is equal to P2 naught minus rho a Z2 minus rho h Z2, whereas P1 naught, you know, this is the absolute pressure in the system, and rho a Z2, that is the density multiplied by the height with reference to over the atom plane at the respective positions. So, now we can determine very straightforward D2 minus D1, that will be equal to minus Z2 minus Z1 into rho A minus rho H. So, this is the equation for determining of the draft. Now, if the column is open to atmosphere, so if the column is open to atmosphere, then D2 will be 0, then we have D1 draft, that is equal to Z2 minus Z1 rho A minus rho H. So, that is what the equation for the calculation of the draft. Now, mind you, we have calculated this draft under the static condition, that is when the gases are not flowing. So, this is a sort of, you can call, this is the static draft. Now, static draft in this particular form, for a given height of the column and given temperature of the surrounding where rho A is fixed, the static draft can be increased only by decrease in the density of the hot gas. That is, when the hot gases are discharged at higher and higher temperature. So, increase in temperature will decrease rho H and hence will increase the static draft. But normally, when this chimney is connected to a furnace, the gases flow, and the flow of gases causes frictional losses, as we have done in case of mechanical energy balance. So, if we apply again the mechanical energy balance at point 1 and point 2 and try to know what will be the say losses, or what will be the draft in presence of the frictional forces, then what we have to do? We have to apply the mechanical energy balance, and as we apply the because we already done the mechanical energy balance. So, I will straight away write down the mechanical energy balance for the flow of gases in a vertical column at point 1 and point 2. So, this mechanical energy balance So, we have to write, I can write down this way, G Z2 minus Z1 into 1 minus rho A upon rho H plus minus D1 upon rho H plus two plus F minus M is equal to 0. Now, what you have to do is that is very simple. In order to obtain this form of mechanical energy balance, it is in terms of draft, the equation of mechanical energy balance which we obtained in terms of absolute pressure, that is P1 and P2, that has to be transformed in terms of the draft by the respective equation which I have given you. That is very simple. You just write down P1 and P2 in terms of draft and replace P1 minus P2 from the original mechanical energy balance, and you will be getting this expression for mechanical energy balance for gas flow system. For gas flow in terms of draft. In terms of draft. D2 and D1, they are the draft. So, this is the equation which we will be using to calculate some of the parameters of the column of gas and so on. F, the frictional forces, and M if there is a pump or whatever the case may be. So, this equation is applicable to furnace openings, ports, design of dampers, because dampers are also the flow control devices in the flue to regulate the flow and so on. Now, also one should consider that this draft is also used, draft is also used to regulate the air during combustion process, Now, for example, say the natural draft, what happens? Suppose we have a furnace, this is the furnace, and from here the hot gases are flowing, and this is the, say, chimney, this is, say, column of hot gas in chimney, this is the flue, this is the flow of POC, go upward. Now, let us consider this is a burner from where air is supplied. This is a burner from where air is supplied, and above the burner we can consider a column say this is a sort of hypothetical column, of cold air above burner. Of the same height as that of the chimney. Now, this is a mechanism where the flow of air through the burner and into the furnace can be regulated by way of natural draft. But with this natural draft, the problem is that if you want to have a very high natural draft, then very high temperature of furnace gases are required. So, the disadvantage for using natural draft as a flow regulating device is that heat exchangers cannot be used. Heat exchangers cannot be used. एक मिनट जरा रोकना. अच्छा ये बता. So, this natural draft is also used or can be used to regulate the flow of air into the furnace, but then the use of heat exchanger is not possible. Now, another type of say draft that we have, that is the induced draft. Induced draft. Now, induced draft, let us again consider a furnace. Say this is a furnace. Here you have the burner for supply of the gas fuel mixture, and here this is the flue, and somewhere here we have installed a fan. This is a fan, and this is the chimney. So, what is done? This is the column of hot gas in chimney. This is induced draft fan, induced draft fan. This is a burner. So, what you are doing in the induced draft, you are no more using the density difference of the gases, but you are putting an extra fan. Now, this fan which you have put downstream the furnace, it creates a suction. So, in induced draft, a fan is used. It may be required to find out the capacity of the fan, the problems we have done. Now, increase in suction is available because you can run the fan, and hence heat exchangers can be used. Heat exchanger can be used. Heat exchangers can be used. That is possible, but the only disadvantage in this type of the disadvantages of using induced fan is, first of all, interaction between hot gases, dirty gases with the fan. Temperature is very high. So, the chances of say destruction of the fan is there. And second important disadvantage is that the air leakage. The air leakage. Now, since the furnace operates under suction, so the chances of air leakage is very, very high. So, one is to be careful, because any air leakage will take away the heat of the furnace, and such calculations we have done in our lectures on combustion 9 to 13. So, air leakage is very detrimental, though the induced draft fan is good, but these are the disadvantages. So, another type of say is the forced draft system. Forced draft system. Now, in the forced draft system, what you do, this is the furnace, again this is the furnace, here you have the flue, and here you have the chimney. Now, what you are doing, say this is your burner, and somewhere here this is now the fan, this is burner, here is again the column of hot flue gas in chimney. So, what you are doing here, you are supplying now air through the burner. So, here higher pressures can be achieved, higher pressures in the furnace can be achieved, high pressure drops are possible. Now, be careful, because in this forced draft system the furnace operates at pressure slightly greater than the atmospheric pressure. So, in that case leakage of products of combustion from the furnace to the environment is very much possible, and which is very, very detrimental. Hence, the forced draft system has to be considered in lieu that the furnace, that there should be no leakage in the furnace, because any such leakage, the products of combustion with CO2 or CO, it may leak and it will destroy the environment. So, to counter this, there is another draft that is called the balanced draft system. Balanced draft system. Now, in the balanced draft system, say again we have the furnace over here, furnace, this is the flue, and here is the fan, and this is the chimney, and here this is a burner. We are putting one fan also over here. So, what we have done, this is the column of hot flue gas in chimney, hot flue gas in chimney. This one is the induced draft fan, induced draft fan. This is the furnace, this is the burner, and this is a forced draft fan. So, the advantage of this is that the pressure inside the furnace will always be balanced. So, the problem which was there in the forced draft system, that the leakage will not be there, but this balanced draft system is a complicated one and it requires several control. Well, these are the 4 type of systems are available to regulate the flow of air during the combustion process.